go back to our slides. Just a short review of what we have discussed last meeting. So we have discussed the intro to reactor design, and we have discussed that the rate equation is an intensive measure. So it's not dependent on the amount of the system in which we are measuring it, and it's a differential equation. Now, as to reactor design, what are the primary objectives rather in reactor design? So we need to determine the size of the reactor, meaning its volume, and the type of the reactor that is best suited for a particular duty or a particular system to be reacted. The method of operation also is a thing to look into, whether it is batch or continuous. Then we discuss about the factors to consider in predicting reactor performance. So we have temperature and composition. So temperature having something to do with the endothermic or exothermic nature of the reaction, whether you need to apply energy or supply energy, or whether there's a need for it to cool down or energy to be rejected by the system. So we also discuss regarding the rate of heat addition and removal to and from the system, and the flow pattern of the fluid through the vessel, especially if the vessel has solids present on it. Then we've discussed the types of reactors, and it was emphasized that our coverage in here, since this is introductory in nature, will only be for the batch and the two ideal continuous reactors, the CSTR, otherwise known as the MFR, or the back mix reactor, and the plug flow or the tubular reactor. Though for industrial processes, we also employ these reactors. Now, we even have the fixed bed and fluidized bed reactors. Now, as to homogeneous reactions where they are effected, so it could be either be facilitated in a batch reactor, it could be also steady state flow or unsteady state flow, otherwise known as the semi-batch process. So this is our batch reactor, this is our plug flow reactor, and these are the various forms of the semi-batch reactor and their various modes of operation. Now, we would like to emphasize that this is our main goal, that we know how to use the performance equation for these three ideal reactors. Then we discuss the characteristics of the batch reactor, primarily suited for small-scale operation, and it has little, if no, supporting equipment needs at all. Okay, no, suited also for slow-paced reactions. For the plug flow reactor, so we have very low maintenance cost for this because of the absence of moving parts, and then the variation here in the concentration is axial by nature, so it's not radial but axial. Compared to the batch, at any point in the reactor, the concentration would be the same. So the same thing with the CSTR, the concentration at any point inside the reactor is the same, and it's best suited for liquid phase reaction and viscous liquids. Now, your continuous reactors can be operated in series or in terms of batteries, whether of similar kind or combination of these two continuous reactors. And we have ended with the performance equations, and they are all anchored upon the mass balance equation. The rate of heat and the rate of mass input is equal to the rate of heat or mass flow out of the system or of the element of volume, plus the rate of accumulation of either mass or energy, plus the rate of disappearance due to chemical reaction. Okay. As for the batch reactor, we have this performance equation, this one here. the time, the holding time or the residence time is equal to CAO times the integral of the dxa over the rate, where the rate is dependent on the type of the reaction. So this is where they're going to vary. You can also simplify it based on this one in here. The rate equal to the negative of dCAdt, wherein we can get also another performance equation form, which is time equal to dCAdt. That is, if you are dealing with concentrations, there's no need anymore for you to convert your concentration information to conversion. That way you can fit in here in the performance equation written. So you can also use this one here on top. Now, for constant density system, wherein the fractional change in the volume is 1, the epsilon A equal to 0. I hope you haven't forgotten about it. So if for a constant density system, your fractional change in the volume is 0, and your formula would be something like this. Okay? So I asked it in this slide, but as to the different form of the performance equation, this would be it. For gaseous systems or varying volume reactions, this would be your performance equation. So you can take note of this very important slide in here that gives you the different forms of the performance equation for a batch system, whether constant volume, the one that you have here on top, or variable volume, the one that you have here at the bottom. Okay? So as to which of the two sets of performance equation you will use, that would depend on the condition that is specified in the problem. That's for our batch system. Now then, because students can, or actually now you can still do this, students are encouraged to understand the graphical implication of the performance equation for the batch reactor. So in general sense, you have, let's say for example, in the horizontal axis, the XA, the conversion, and on the vertical axis, you have the product of the reciprocal of the reactor volume and the rate. So the area under the curve, this is the curve, okay, between, this would be the resulting curve if you're going to plot XA versus this one. This would be your curve. The area under this particular region from XA equal to 0 to XA at any particular time will be T over NaO, or the holding time, the residence time, divided by the initial number of moles of A. This is in the general case for your batch reactor. In here, you have two graphs. One is in terms of conversion, the other one is in terms of concentration, as you can see. So you have on the vertical axis the reciprocal of the rate. If you're going to plot this one, the negative 1 over RA versus XA, or 1 over RA versus CA, you will have the area under the curves as follows. So for in terms of conversion, we have T divided by CaO as the area, but in terms of concentration, this area is simply the time it would take for the initial concentration CaO to lower down to Ca. Okay, in the case for constant density system, which is the usual case if it's a batch reactor, because normally we have liquid phase reactions facilitated in a batch reactor. And for those reactions, most of the time class, it's constant volume or constant density. So this would be the graphical interpretation of the areas under the curve of these two variables that are being plotted in here, or paired and plotted. Okay, of course, you're not going to do graphical, you're going to do everything analytical. graphical. So that is why this is not given much emphasis during the discussion. But nonetheless, that's how it's to be interpreted using the graph. Now from figure 2 in here, these are the things that we can take in terms of important principles that you need to take note of based on figure 5.2. So the reaction rate RA has been left as an algebraic symbol in the previous expressions. So in the special case, there will be an algebraic relation in terms of concentrations and the rate. Example, you have here the rate and concentration. So for batch system, constant density means constant volume, and you can use either concentration or conversion as a variable for monitoring the progress of the reaction. Okay, as you can see in here. Now, let's leave batch system. We now go to continuous systems. And for these continuous systems, there are two characteristics that you need to understand and you need to know because these two will be associated with the performance equation of these systems. Okay, now one of these characteristics is the space-time or the tau. Now, it's the reciprocal of the space velocity. Space velocity is s. Okay, it's not seconds, but rather s. Now, how do we define these two important concepts or characteristics of flow reactors or flow systems? So, when we speak of the tau, it's the time required to process a one reactor volume of feed measured at specified condition. How long will it take for your reactor to process one reactor volume of feed at specified condition? That is your tau, or we call it the space-time. It has, of course, the unit of time. The reciprocal of the space-time is the space velocity s. Now, the space velocity accounts for the number of reactors that can be processed, or the number of reactor volumes that can be processed per unit time. So how many reactor volumes can be processed in an hour? So that measure is the space velocity. Whereas the space-time is how long will one reactor volume be processed. This one is how many reactor volumes can be processed per unit time. And as such, the unit is per unit time. Now, you can see here that tau has the formula equal to CAO times B times FAO. Now, I will define FAO because this is, I think, the first time that you will encounter this one, because FAO is only associated with continuous or flow reactors. Now, FAO is the molar feed rate. Molar feed rate, so meaning its set of units is mole per unit time. Pound mole per hour or mole per second or mole per hour. So that's molar feed rate. Now your tau, your space-time, can be solved using this formula, or it can be solved using this formula in here, wherein it's the volume of the reactor divided by the volumetric flow rate of the feed as it is entering your system, whether it's Cstr or PFR. Now, you have these two alternative formulas for tau. And this FAO, by the way, class, I'll write it here. That way you will know why from this particular formula, you have this one now for the tau. The FAO, oh, excuse me, class. The FAO is actually the product of the volumetric flow rate and the initial concentration. So your FAO is volumetric flow rate, the small v with the subscript O, times the initial concentration. And as such, you would see here that if FAO is changed to this one, so you will have tau equal to CAOV over this one, small v sub O CAO. So the CaO cancels each other and you will have V over V sub O as another formula for determining the space-time. Okay? You have your space-time using these two formulas. You can solve the space-time using the two formulas that are shown. Now, so we will first tackle the CSTR. Okay? If in the batch reactor class, your formula for determining the holding time or the residence time needs you to integrate for the CSTR or the MFR, you don't need to integrate anymore. But before I show to you the performance equation for the CSTR, now for this continuous reactor, the same thing with the plug flow reactor, what particular term here or terms here in your mass balance equation in here. So we go here. What particular term or terms in this general mass balance equation will you set to 0 if we talk about continuous reactors? So it is applicable to CSTRs as well as it is also should I say applicable to PFRs. So what term or terms will you set here to 0? You can place your answer on the chat box. What term or terms can you place here to 0 or should be really 0 for the continuous reactors? Accumulation and rate of disappearance. Accumulation. Okay, so the answer is accumulation. For your continuous reactors, the CSTR and the PFR, it is the accumulation term that is set to 0. There is no accumulation because the rate in which your feed is processed into the tank, it's the same rate in which that particular processed feed leaves the tank already. So there is no accumulation at any particular time in your CSTR. Same thing with your PFR. Otherwise, your reactor will either go dry or will overflow if there is accumulation. So duwa lang man na. If the rate of input is greater than the rate of output, then it will overflow. But if the rate of input is lesser than the rate of output, it will go empty or it will dry up. Okay, so there is no accumulation for your continuous reactors. So the two continuous reactors that is. So correct for those who have answered accumulation. Okay, so we go to our CSTR. This is our CSTR. So assume rate of flow in is equal to rate of flow out. So if the rate of flow in is equal to the rate of flow out, then we say that there won't be any accumulation. And in terms of the molar feed rate, now this is your molar feed rate FAO. So FAO, you see it here at the inlet, and you have FA at the outlet. So your FAO is V sub O CAO, whereas your FA, this is already for partly converted feed. You have V sub O, small v sub O specifically times the concentration of A. You see that it's already concentration of A, meaning part already of the A was converted. Now, V sub O is the volumetric flow rate, which has the unit volume per unit time. Now, for our CSTR, since it has no accumulation, your input would be this one. I have to enlarge so you will see. Please interrupt me if you have any question. Your output would be FA, and FA is FAO times the quantity 1 minus XA. Your reaction is the rate, product of the rate times the volume. So since there is no accumulation, you could see in here that input is equal to the output. This entire thing is output plus the reaction, loss due to the reaction. So this is rate plus the product of negative R sub A V. Now from in here, if you will have this expanded, you can cancel the FAO and the FAO in here, leaving you with a negative FAO XA in this side, which you can readily transfer on the other side. So that would be your FAO XA here, leaving in the other side the product of negative R sub AB. So this is the reason why you have this. If it's going to be written from an equation taken from here, this would be actually 0 equal to negative FAO XA plus negative R sub A times B. So I'd like to place a parenthesis on this. So that is why you place this one in here and then interchange the variables. So you have the constants here, the volume and initial molar feed rate. So they are constants. They are set on one side and you have the variables here. So conversion will be varying with respect to time. Of course, this rate expression will be varying because concentration of A will also be varying depending on the time elapsed. So the constants on the left, then you have in here the variables on the right. If we will have it expressed in terms of tau from in here, we will get the expression in terms of tau. You can see that your V over V sub O, small v sub O CAO, is equal to XA over the rate. Okay? Now this V over V sub O, small v sub O, is the tau, and that has a unit of that's the reciprocal of the space velocity. So you have 1 over s here, and that's equal to dCAO you cross multiply on the other side, on the right side. So you will have CAO XA divided by the rate. That is now your tau. Now if I will erase everything in here and emphasize to you the working equation, performance equation for the CSTR, this would be your performance equation for the CSTR, expressed in terms of space-time, just like the way we have expressed the performance equation of the batch reactor in terms of time. Only that in here, we have space-time. In the batch reactor, we have the residence time or the holding time. Okay? Later on, you will see that there will be a condition wherein your T, the residence time in the batch reactor, can also be represented as the space-time, the tau. As to what that condition may be, that will be discussed in the succeeding slide. So this is your second performance equation. So this is your performance equation for a CSTR. And it's also expressed in terms of time. We proceed. So I have already here highlighted the performance equation for your CSTR. So again, there will be an algebraic, so this is just an algebraic relationship in terms of concentration and the rate in here, the rate law for each specific case because your rate can be this one if it's first order. Example, e.g. example, rate is first order, so it's represented that way. If it's second order, then you will have to change it to this one. Or it could even be K, C, A, C, B. You just have to express B in terms of A. That way you can process everything. But since in this case, class, by the way, since you don't need to integrate, it's purely algebraic in nature, you need not, I'd like to emphasize, you need not, you are not, it's not suggested that you express the concentration terms here in your rate law if there are several species in terms of one species only. It's because you can separately account or determine each of the concentrations and just simply multiply them afterwards because there's no need for you to integrate. But in the case of the batch reactor and the PFR, there's a need for you to really express all concentrations, all conversions in terms of one species only. because you are integrating. In here, there's no need. But if you want to, then that would be still okay. Okay, but it will add more computations and time in your solution. Now, for a well-mixed reactor, the concentration is the same at all points inside the reactor, and it is equal to the outlet concentration. So if I will write here C sub A, the concentration inside the reactor at any time, that should be the same concentration of the fluid that leaves your reactor, or of the system that leaves your reactor. Okay? Now, I'll clear my markings. Just interrupt if you have any questions. Now, as to the graphical interpretation of the CSTR, so you have here the graph of XA against the reciprocal of the rate, and you are also having it here against CA against the reciprocal of the rate. So the area in here on top of the curve is the V over FAO. This area is the V over FAO, which is also equal to tau over CAO. Now, in here, in the other side, your area is the space-time itself, this one on top. The space-time, which is VCAO over FAO. This is for constant density systems. If you plot concentration or the reciprocal of the rate versus concentration. So this is your plot. You will right away determine the tau based on the area on top of the curve. While if it's in terms of conversion, this would be the area that you will be determining. You don't still determine the tau, but after you have determined the area, you just multiply it with the initial concentration. That would already be the tau of your system. Okay, so this is the graphical interpretation of the working equation that we have for the CSTR. Now, if you're going to compare the two that we have finished discussing, so the batch versus the mixed flow reactor. In here, there's a need for you to integrate. In here, there's no need for you to integrate. Okay, so tau is equal to CAO XA divided by the rate, whatever is this rate. All you have to do is plug in all the infos there because this is algebraic in nature. There's no need for you to integrate. Okay? Any questions so far? There's none. Then we go to the last of the three ideal reactors, still classified as continuous, and that's the plug flow reactor or the tubular reactor. Now in here, we select this differential volume of fluid element in your tube or in your plug flow reactor. So volume coming in is V and the volume coming out is V plus this delta V. Okay, that's for our plug flow. The initial molar feed rate is still labeled as F sub AO, and the final molar flow rate is F or FA. Now, how do we write the performance equation for this system? Okay, I'll go here. So the performance equation for our plug flow reactor where there is no accumulation is similar, like 99% or 98% similar to that of the batch reactor. Why am I saying that? So let me just... Now, you have here 1 over FAO times the integral of dV integrated from 0 to V. Here on the left side, and on the right side, you have the integral of dXA divided by the rate law, whatever the rate law is, integrated from 0 to the final conversion X sub A. If this is integrated class, that would simply be the V, because this is V, then you substitute the limit 0 to V, that would be V. And as presented to you also in the CSTR, that is V over FAO is actually tau over CAO. Now, this means that these expressions here that you have on the left can be all equated to the same thing. Okay, they can all be equated to this. And if this CAO is transferred here, it would be tau equal to CAO. I'll use this one, integral from 0 to XA or XAF of dXA over the rate. If your memory is that good, this is the same performance equation that we have for our batch reactor. Where is the difference? The difference is in here, because in the batch we have this as time, T. But for the PFR, we represent it as the space-time, or that is the tau. In the same way that you can write this also as the integral from CAO to CA of negative DCA over. Okay? Exactly the same as that of the batch. The only difference is the representation of the time. The time it would take for your reaction to reach this final concentration or to reach this particular conversion. Now, this is your performance equation for the PFR. So you only have three performance equations to take note of for the batch, which is similar to the PFR, and for your CSTR, where there's no need for you to integrate. Then just add to that the formula for determining the tau. Okay, the tau formula, which is either B over V sub O or CAO V over FE. Okay. Any questions before I give you just one sample problem before we part ways today? Yes? No question? I hope there's none. If there is, you have the chat box to use if your connectivity will not allow you your voice to be heard. Okay, so no question. We will have this. So the problems that we will be discussing in this first of the 4 slides on reactor design will be concentrated only on one particular type of reactor for a single reaction. So we won't have multiple reactions in here. Okay? Now, sample 1 talks about a 1 liter per minute of liquid feed containing A and B. So the initial concentration of A is 0.10 mole per liter and that of B is 0.01 mole per liter, which flows into a fixed reactor, rather a mixed reactor of volume 1 liter. The materials react in a complex manner for which the stoichiometry is unknown. So we are not provided with the stoichiometric equation or the chemical reaction. The outlet stream from the reactor contains A, B, and C with the concentrations indicated. So for A, you have 0.02 mole per liter left. For B, you have 0.03 mole per liter left. And for C, you have 0.04 mole per liter. Okay, it's shown in the figure. Find the rate of reaction of A, B, and C for the conditions within the reactor. Meaning with the conditions that are stated in here, we are to determine the rate of A, B, and C. So before we try determining the required information, can you tell me what particular rate is being asked in here? Is it a rate equation, a rate law, or a particular quantity? So the rate that is being asked here is a quantity. Is it a quantity, a differential equation, or a rate law? Okay, somebody wrote already. A value. Correct. A value. Correct. So if it's an equation, it would really specify that it's a rate equation. Okay? Seldom will the problem require you, especially related to reactor design, seldom will it require you of the rate equation. Although there are, but it's very seldom. Most often, it would be asking you already for the actual value because you are asked of the rate when it's just a pure kinetic problem. But if it's already needed in reactor design, uh, it's supposed to be that you know already the rate. Or you can determine the rate based on the performance equation. Okay, so you're right. You are asked for the quantity or for the actual values of the rates of A, B, and C. So I'll go to the Jamboard and check. Okay, so this is our Jamboard. So we will write the given information. Oh, sorry, class. Okay, so let me go back to the problem. So you're given 1 liter per minute. 1 liter per minute. So you're in the same statement, there is a mention that it's a mixed flow reactor and it's already provided in the illustration. So we have a mixed flow reactor. That's our mixed flow reactor, and you you are given that 1 liter per minute of liquid feed is being processed. The initial concentration of A is 0.1 mole per liter, and that for B is 0.01 mole per liter. I'm just rewriting it here based on what we have in the problem. It says there that the volume of the reactor is 1 liter. So I'll place it here. The materials react in a complex manner wherein we don't know the stoichiometry, but we are provided with the final concentration. So Ca, Cb, and C sub C. So I will eliminate the F already. It's already known to us that if it's just Ca, then it's the final concentration. So 0.02 mole per liter. And for the B, we have 0.03 mole per liter. And for C, we have 0.04 mole per liter. Okay, and that's it. So you are required to determine the rate of reactions. Now notice the way I write it, class. I'm just used to having A and B as my reactant. So I'll place negative. And I'm used to having C as one of my products or my salt products, so I write it as positive. But actually, since we are not given the stoichiometry, we do not know. We do not know whether B is product or whether it's reactant, nor C is product or reactant. Same thing with A. But since I'm just accustomed to having write it like this, so I just write it that way. If my answer later will be negative, then my assumptions are wrong. So for example, if I'll get a negative R sub A here, which is negative, then meaning A is one of the products or is a product because my answer is negative. If my answer is positive for R sub A, negative R sub A, that is then meaning my assumption is correct, that A is a reactant. Okay, so this is an MFR or a CSTR That tells us that our working equation will not need us to integrate. So our working equation is T, or our tau in this case, because we have a flow reactor, is equal to CaO XA over the rate. Okay? And this particular tau is equal actually to V over V sub O. So we go back to our problem and check whether we have the V over V sub O. You can see that we have it in here. So meaning this is already equal to 1 liter divided by 1 liter per minute, giving you an answer for the tau which is 1 minute. Okay? Now, we go to determining the CaOXA and the rate in here. So first I will have, of course, I will determine the rate. Now, what is the CaOXA in the first place? I will transfer the rate expression in here, and this tau, which we determined already as 1 minute, I'll place in here, meaning I switch the two. So I will have here 1 minute, and in the numerator, I need an expression, an equivalent expression for CaOXA. What is that? That's CaO minus Ca. How did you come to know about it? This is the amount of A that has reacted, right? The amount of A that has reacted. What is the amount of A that has reacted? It's its initial concentration minus its final concentration. The initial amount, which is higher, minus the final amount, will give you the amount that is lost due to reaction. So meaning it's the amount that was lost due to reaction. So in this case, we will substitute the CaO and the Ca that is given in the problem. So CaO is 0.10 and Ca is 0.02. So I'll place here 0.10 minus 0.02. This is mole per liter. And this is 1 minute. So my answer here is 0.08 mole per liter per minute. Now, since my rate for A is positive, my assumption that it is a reactant is correct because it's positive. Should have been this one negative, then the assumption that A is a reactant is wrong. A then is a product. Now, we use the same formula for the other species in our reaction. So, for another equation, we have tau. This time, we'll talk about CBOXB. And we have here the rate in terms of B. We still have the same tau, so I will write na lang 1, or shall I say I'll have it written like this so we can right away determine what we want to determine. So we'll have the rate in terms of B is equal to, just like what I have done here, it's CBO minus CB divided by the time, which is 1 minute. We just interchange the CA and the tau. In this case, we interchange the CB and the tau. So CBO and CB will be subtracted in the numerator. So CB is 0.01 and CBO is 0.01 and CB is 0.03. So 0.01 minus 0.03. So mole per liter, and this is 1 minute. Okay, what is your answer here? Negative 0.02 mole per liter per minute. What does this tell you? It's negative. Therefore, right here, therefore, B is a product. And it should be R sub B equal to the answer that we have here written as positive. 0.02 mole per liter per. Any question? Okay, none. Then we go to the last. So the same principle behind the same form of equation. So I will just go straight to the equation. We assume that C is the product. So I'll write R sub C is equal to CCOXC over the tau. I already interchanged the two. What is CCOXC? Remember, this CCOXC is the amount of C formed. It is an assumption that it is a product. So then we will have a different formula in the numerator. The final amount of C minus the initial amount is the amount that was formed. So divided by tau. So the final amount of C, 0.04, and we don't have any C here. Okay? So 0. So we have 4 minus 0 over 1. So your R sub C is 4 mole per liter per minute. So it's a product. Our assumption that it's a product is correct. So in terms of what the problem requires, this is it. There's no need for us to integrate. Okay. The B is on the next page. So we determine the rates easily. So that's for B. This is for A. This is our A for the A that is 1. Okay. Now from in here, from the rates of R, B, and C, we can actually write tentatively the stoichiometry. So it would be something like A forming B plus C. But we don't have yet here the coefficients, right? We still don't have the coefficients. Now, anybody who knows how we're going to determine the coefficients? In this problem, it's not anymore asked. But actually, we can determine the stoichiometric reaction based on the values of the rates that we have. So anybody who knows what should be written here? Or how do we determine what should be written here? Would you know how to write the correct coefficients here based on the rate? So I'll write here R sub A is equal to 0.02. R sub B, wait please, excuse me. R sub A is 0.08. R sub B is 0.02. So this is 0.08. This is 0.02, and R sub C is it 4 or 0.04? It's 0.04 plus. Sorry. I was wondering why it's a whole number. The others are just decimal. So this is 0.0. So I write it here. What do you think should be, how should we use the rates in terms of the coefficients that should appear written on the species A, B, and C in the stoichiometric equation? How do we do that? Okay, I think nobody has an idea. So what you do, you take the ratio. Okay, ratio of the rate of A to B is 0.08 to 0.02. So meaning you have 4 rate in terms of B. So what does this mean? You have 1 here and you have 4 in here. Okay, what about rate of A in terms of C? So rate of A is 0.08. In terms of C, it's 0.02. So you have here, wait, B, R and B, R, sorry, 4. Sorry, class, it should be 4. It's crowded there. So we'll have rate of A to C is equal to 0.08 divided by 0.04. So this is 2. So rate of A is twice of the rate of C. So I'll place here 2. Okay, 1 is to 2. Now what about B and C? We'll check. So rate of B, rate of C. So rate of B is 0.02. Rate of C is 0.04. So this is 1/2. This tells you that R sub C is twice of R sub B. Correct? The rate of C is twice of B. So you could see here, this 4 is twice of this 2. Is twice of 2. So from the values of the rates, should you be asked to deduce or arrive at the correct stoichiometric equation? This is the stoichiometric equation. It's not being asked, but that's how you find it. So A forming 4 moles of B plus 2 moles of C. You get it? Any question? Okay, there's none. Sige. It's already 1:31. I'll just recheck. I'll stop sharing here. And let me just go back to the slide. Okay, just a few minutes. So the key points that we will learn from this first example are the following. So this example demonstrates that we can observe the reaction rate in a mixed flow reactor by observing the steady state concentrations. Steady state concentrations going in and out of the reactor. So we simply determine the CAO and the CA, the CBO and the CB, and the CCO and the CC. We do not even have to use stoichiometry for observing this, but as what I have illustrated to you, the stoichiometry can also be deduced or taken from or arrived at using the values of the rates. So observing the reaction rate does not mean you obtain a reaction rate expression or a reaction mechanism. It simply is requiring you to determine the actual value or the quantity of the rate. Okay? So that ends our lesson for today on the sample problem on the CSTR. We will continue this again, class, tomorrow. Okay, after which you will be left with the rest of the time to process your problem sets. Do you have any question?